All right, so this talk is about Fabric Private Chaincode, and as the subtitle already suggests, this is about smart contracts with confidential computing in the context of Hyperledger Fabric. So to begin this talk, let's try to make this very interactive. And can you write a +1 or a plus in the channel if you have ever heard of Hyperledger Fabric before? And I'm wondering how I can see that chat channel. There's a +1. Awesome. There are more pluses coming in. That's great. Okay. However, I think it's still good that we start at the beginning and quickly talk about Hyperledger Fabric first. So Hyperledger Fabric in just a single slide. So Hyperledger Fabric is a generic blockchain platform which allows you to build a permissioned or a consortium blockchain system. It's developed under the Hyperledger open source community. Hyperledger is, I would say, very similar to the confidential computing consortium, but just for enterprise blockchain systems. There are many other components developed under Hyperledger, and Fabric is one of the components developed there. So in essence, a Hyperledger Fabric blockchain network consists of, I would very briefly say, 3 components. We have clients, we have Fabric peers or nodes, and an ordering service. The clients are communicating with their Fabric peers in order to trigger the invocation of a smart contract, or in Fabric speak, a chaincode. And the chaincode then performs some computation defined by the users upfront, accesses the world state, and returns back the result of the computation back to the client. The client does this with a couple of peers usually. They're also called endorsing peers, which are actually saying, okay, look, if I send my transaction to multiple peers for execution, let's see if they all return the same result. If this is the case, the client crafts a transaction, sends this to the ordering service, and then the ordering service puts this transaction in a block and distributes the block among all the peers on the network. When the peers receives a block with those transactions, they validate and commit those transactions to their local view on the ledger. And this is, again, just in a single slide, a distributed technology called Hyperledger Fabric. So there are many use cases which are, let's say, very happy about that distributed ledger technology. In particular, the interesting part is that what you get from such a system is a verifiable aspect. That means if a participant in the network is not happy with a transaction which is on the ledger anymore, he can, of course, delete it from the ledger, but he cannot delete it from the replica of the ledger of the other participant. So at some point, once something is committed to the ledger, everyone knows about it. You cannot change the history. So this is a nice property, the verifiability aspect. However, there are more aspects when we talk about blockchain use cases, and in particular when we talk about privacy-sensitive use cases. You could imagine that there are loads of different use cases, which, for instance, like an auction or a voting system, which builds on top of that distributed ledger in order to give additional insurance that, for instance, a ballot has been committed, and that nobody can later say, okay, my ballot was not used in an evaluation of the voting. So that's very nice, and the blockchain gives us that. However, there's also that crucial privacy aspect for that particular use case. So for voting, for instance, we all understand that the secrecy of our ballot, or our content, our vote, has to be maintained secret, as long as the voting process is not done, or it should be secret forever, right? Other use cases also come with strong privacy requirements, in particular when we are looking into the healthcare area. I mean, we have seen in the previous presentation by Andreas that there's definitely some need of confidentiality when we talk about patients' data. But also in supply chain use cases, there are situations where we do not necessarily reveal all the informations of a good deal we made with a business partner, right? Luckily, Hyperledger Fabric comes already with a bunch of mechanisms built in to address those issues. For instance, there is the concept of channels, which allows us to, let's say, partition the blockchain into multiple channels so that only participants who are actually relevant for a specific application, let's say, are part of the network or part of that channel and can see all the related data. Private data collections, for instance, is a mechanism which allows us to just store a hash of the data on the blockchain and then disseminate the data in an offline fashion among all the required participants. A transient field, as the last mechanism here, allows us to send data to a smart contract without having the actual data later end up on the ledger. So that is, for instance, used when we think about, hey, the chaincode smart contract could actually encrypt data. We use the transit field to provide the encryption key for the data, and then all good, right? However, all these solutions, they have one problem. And the problem is the data visibility at the endorsing peers. That means the data visibility of the peers which are executing our smart contract. And that also means that not only the peer, but the entire organization has access to that data. Coming back to the voting example, if the government would run such an endorsing peer and we send our ballots to that smart contract, they are encrypted. At some point, that smart contract needs to decrypt in order to evaluate. But when that peer decrypts the data, it has access to the clear data. For a voting scheme, this is clearly not ideal. I think we all agree on that. In the chat, I read something about, hey, what about homomorphic encryption, things like that. Yeah, there are active research. There's an active research community exactly working on that front. However, in this context of this presentation here, let's talk about confidential computing as an alternative solution. So, and this is why I would like to talk about today about Fabric Private Chaincode, which is a framework to build, deploy, and run private chaincodes on Hyperledger Fabric, which exactly addresses those strong privacy requirements as we have discussed in the previous slide. And we do that by executing our chaincode using hardware-based trusted execution technology, in particular Intel SGX. By using this confidential computing technology, we essentially get three, let's say, additional properties, three security properties to our blockchain system. The first one is confidential compute, which means that all the transactions and the ledger only contain encrypted data. The second is verifiable operations. That means that all the transactions are in the end are verified through attestation, which was already mentioned before in the introduction by Felix. And the last property is data misuse prevention, which means that only the trusted execution or our particular chaincode can use the data which it belongs to, essentially. So let's have a look what we do get here in this case from using hardware-based trusted execution. So essentially what we are getting is here that we, with the help of Intel SGX in our case, we're reducing the TCB dramatically. with a normal Fabric peer, the assumption is, okay, if I execute my chaincode on a peer, I need to trust, of course, the chaincode, but also the peer, the operating system, the hypervisor, the hardware, the administrator of the peer, even maybe the entire cloud company where this peer is hosted. Well, this changes by using Intel SGX, where we actually now draw the security boundary just around our chaincode, our application, and the data what we would like to address. Of course, we are still assuming, or we still have to trust in the actual hardware, but we definitely reduce the TCB dramatically. The three properties we get from trusted execution technology, like were also mentioned before, like confidentiality, integrity, and verifiability. However, just by running the chaincode itself inside an enclave is actually not enough. So we will see that in an overview of our architecture. So what you can see here is, this is more or less what you saw on the Fabric slide, is we have the clients on the left side, we have the Fabric peers here, and the ordering service. So what we are going to do here with Fabric Private Chaincode is that we take our chaincode, execute it in Intel SGX enclave. But in addition to that, as I mentioned, we have to add a little bit more to the table. In particular, on the client side, we need to add a component which, of course, needs to be gives the client a tool to communicate with that chaincode and integrate that in its application. This is done by our FPC client SDK. And what it in particular does, I mean, or the most important thing is to it is responsible to encrypt the communication between the client and the chaincode enclave in a way that only the chaincode enclave and not the peer can access the data in clear anymore. What we also need to do is that we need to embed the information, what is our intended chaincode. So in SGX, we have that concept of a hash over all the code and data running inside the enclave called MR enclave. And what we're doing here is that we integrate this in a so-called chaincode definition, which has to be agreed by the consortium, by the users of that chaincode, before we're actually launching and spawning our enclaves. In addition to that, we need a few components which we integrate in our attestation infrastructure. So we introduce an FPC enclave registry, which is responsible to maintain the identities of our enclaves, which essentially tells us, hey, what peer runs which enclave, which chaincode is executed by that particular enclave, and so on. Interestingly, since we have a blockchain system, we just store this information on the blockchain, right? In addition to that, we have the FPC enclave validation, which is essentially a component which helps us to verify that the transaction was actually computed or executed by an SGX enclave. As I mentioned before, I think I screwed up here the order of my slides. We have that protected communication between the client and the actual enclave, but also we have to make sure that all the data which is consumed from the untrusted word state from the peer by the chaincode inside the enclave is encrypted and authenticated. So let's talk a little bit about how do you use that Fabric Private Chaincode now. Okay, so essentially when you are familiar with Fabric, you know you can develop chaincode by just implementing an invoke function and compile that stuff and ship it to the peer for executing. So with Fabric Private Chaincode, this looks a little bit different, not much, but since Fabric Private Chaincode builds on top of the Intel SGX SDK, yeah, we have to write our chaincode in C, C++. Maybe this is not ideal for a chaincode language. I don't know. However, our framework provides us now the capability through an FPC shim to protect all the inputs and outputs, and by encrypting and authenticating it, and also the word state, as mentioned before. That means if the user performs a get state or put state operation, FPC takes care of encrypting and authenticating the data all in background before they're leaving or entering, before they're leaving the enclave. The FPC framework also makes sure that the response generated by the chaincode is signed, and this signature corresponds to an attestation which is stored in our enclave registry. So you may notice that I've complained a little bit about the C, C++ chaincode, and yeah, so that was actually also the feedback we got from the community. So there with normal Fabric, there is Go and Node.js and Java chaincode, and now we're adding here a new language on the stack. This is not, I mean, it's fine. However, if you have already implemented some chaincodes in, let's say, Go, well, you have to re-implement everything from scratch. Not ideal. And this is why we were actually looking into something else. And this is Fabric Private Chaincode plus the Ego framework from Edgeless system in order to extend our support for to FPC now also for Go Chaincode. How does it look like? So essentially, what you now do is you take your traditional Go Chaincode, which it depends on your personal preference, looks now a little bit nicer or not, right? You take your Go Chaincode, and we still hide all the complexity, as I mentioned before, behind this shim chaincode stub interface. So the end user does not need to care about the encryption of the data when he performs a put state or get state operation. As mentioned, we use the Ego compiler to build and then run the FPC Go Chaincode. The most fascinating for me on this particular project is that this was a contribution by a student here from Switzerland who provided the initial contribution as part of his master thesis. So Ricardo, thank you so much for that contribution. This is awesome work. However, since we are still working on that, this feature is currently tagged as experimental. So let's have a quick look what you need to do in order to use Fabric Private Chaincode now.
Okay.
So
Markus, I'm so sorry to interrupt you.
Yes.
I'm so sorry. We're a bit behind in time, and so your 20 minutes are over right now, and that's why we have to be hard in order to stick to the agenda. But you are in an extended Q&A later, right? So during the break, you're in a session, and whoever has questions about your topic can come and talk to you about your talk. Is that correct?
Yes, awesome. So
that's correct.
Yes, let me just finish here. So everything is available on GitHub. Everything is open source. Please visit us on GitHub. We are also on Discord. And as mentioned, I'm also happy to join this extended Q&A session to answer more of your questions. Thank you.